Kia ora, my name is Elodie Bousbib. I'm a postdoc at IEEE, and today I'll present a paper that we wrote with Gilles, CNRS researcher from Sorbonne University, about understanding and mitigating uncounted type of haptic devices failure modes in VR. First, let's start by defining the whole concept of uncounted type of haptic devices. Let's picture a potential interaction in VR with the user's bare hands unencumbered and free of any contraption. The user is free to interact with any of these three virtual teapots. In the real world, the user would ideally interact with the real teapot, sharing similar properties as the virtual one. But what if the user were to interact with the second green teapot? A conceptual robot would encounter the user with his desired teapot at the correct position. Here, the robot displays it at that second location. We've recently seen a huge burst of ETHD designs of really various types, which I won't detail. Uncounted type of haptic devices are conceptually really close to the ultimate display, and yet, while there are various implementations, they're still not deployed outside the lab. But why is that? Why are there that many designs? Why aren't these instances more deployed? Basically because there's a lot of criteria to consider to design them, many challenges, many limitations, and a lack of guidelines. The aim of this paper is therefore to provide a groundwork for ETHD designers. We analyze and highlight the ETHD potential failures and define how to mitigate them to finally justify their lack of deployment beyond the prototype and actually encourage it. For this matter, we used a common approach from industry and quality control, the FMEA, failure modes and effects analysis. Failure modes are ways in which the system might fail, and effects analysis is the studying of their consequences. Why? Being an ETHD designer myself, I aim to help others understand the challenges of ETHDs, their compromises, and define proper guidelines for uncounted type of haptic devices. How, using the FMEA approach, we discuss all the strategies from the literature and therefore finally provide a survey of ETHDs. From the FMEA approach, we first identify the requirements of uncounted type of haptic devices. Let's draw a schematic of the ETHD scenario steps. So first, we have an object of interest in the virtual environment. The user wants to interact with it. The ETHD will then displace itself to physically overlay it. The ETHD principle is to physically encounter the users to provide haptic feedback for the interaction to occur. But what if we have multiple OOI, objects of interest, in a non-deterministic scenario where the user is free to interact with any of them? Which one of these teapots will the user be interacted with? We therefore need first to capture the user's intention, identify which object to overlay, and predict it prior to interactions. All failures and strategies associated to these requirements are detailed in paper, and I will focus here on the prediction resolution. For instance, a failure in the algorithm resolution would result into the wrong object to be overlaid. A potential solution is to mitigate this effect by increasing the number of interfaces and creating swarms of mobile platforms. So without having to predict intentions, robots can be in charge of overlaying each object within the user vicinity. This was instantiated in Zomos here, where the user's next interaction is captured and swarms of robots physically overlay the appropriate role. Now, let's assume that the OOI has been correctly picked. The user will then move towards it, and the ETHD will therefore be required to physically encounter the user. This would require speed, accuracy, precision, and safety. Let's give some examples of some failures and associated strategies from the literature. For the safety requirement, the main risk is to have the user and interface colliding. The first mitigation solution would be to split the user and ETHD workspace. A second one would consist in notifying the users when the ETHD is in place and ready for interaction. Regarding speed, if the interface isn't fast enough, this would result in a spatial mismatch. The interface does not overlay its virtual counterpart because of its spatial position. A solution can be to add a delay mechanism when the user speed is too fast so that they can slow down. We can note that this displacement success is typically a compromise with the user intention algorithm delay when one is applied in non-deterministic scenarios. For instance, here in Turkdick, the participant could not cross the virtual environment because of a lack of platform and a fire sparkling below him. For speed and accuracy, many graphics techniques were employed where the user's trajectory is altered without the user noticing it. Here, it is, for instance, increased to let some time for the interface to reach the objects of interest position. These types of techniques can even change the OOI position to tackle speed and accuracy limitations. More details are available in the paper. So we've first seen the intention, then second the displacement. Now let's focus on the final part of the ETHD definition, providing haptic feedback. So for the user experience to be consistent, the robot is required to provide the appropriate haptic feature to the user during interaction. The ETHD is required to display adequate object properties and enable their associated exploratory procedures. Solutions to enhance visual haptic consistency and the rendering of various haptic features are then proposed and detailed in the paper. So we first decompose interactions with ETHDs through three main steps: intentions, displacement, and interaction. We then used an FMEA approach to analyze ETHD failures and highlighted strategies to mitigate them. The contributions of this work are a groundwork for ETHD designers towards the deployment of these interfaces, a novel framework to analyze ETHDs, a survey of current ETHDs, and an overview of existing ETHD challenges and potential strategies to mitigate them. Thank you for your attention, and check out our paper.